Okay, this video is for lesson 6, which is where we get to use the and rules together, tree diagrams as a solving technique, and Bayes formula. The videos for just the and just the or separately, they're useful in some cases, but very frequently use these ideas together, and so we can solve a much wider range of problems. So let's get right to it. Problem 1 says 2 cards are randomly selected from a standard deck of 52 cards. What's the probability that one card will be a 5 and the other card will be an 8? So you can pause the video, try the problem, and then unpause. Okay, so when I look at this problem, I'm thinking there's really a couple ways this can happen, right? We can have the first card can be a 5 and the second card can be an 8, or separately, starting fresh, we could have the first card be an 8 and the second card could be the 5, right? So throughout this video series, I'll use kind of a shorthand for this kind of a situation. I might just write it this way. The first one's a 5, the second one's an 8, or the second one's a 5, or the first one's a 5 and the second one's first one's an 8 and the second one's a 5. So there's a couple things understood. And that is that if I put things next to each other, that means and, right? So we're going to multiply in that case. And if I have separate cases like this, it means we start over fresh on the other side of an or statement like that. Right, so to do the probability of 5 and 8, technically that's this. That's the probability that the first one is a 5 multiplied by the probability that the second one is an 8 given that the first one was a 5. So I could write it with that. And again, that's really going to mean the first one's an 8, or sorry, the second one's an 8 given that the first one is a 5. So that's a conditional probability. Right? We would multiply because we multiply for and, but the second one's a conditional probability. And then we would say plus because we're talking about an or. It could have been that the first one was an 8, and then we'll multiply by the conditional probability that the second was a 5 given that the first one was an 8. So I'll write it this way. Right? It really means that, that in specific order those things happen. All right, so what is the probability that the first card would be a 5? Well, there are 4 5s in the deck out of 52. If I draw that card out, right, it doesn't say anything about replacing that. We're drawing 2 cards randomly, or if you want to think of them being drawn at the same time, you could think of that as equivalent to drawing 1 card and then drawing the second card, but not being able to get the first card, so it's without replacement. And that means that the second card, there's only 51 cards left in the deck. That handles the condition that the first one's a 5. And then I have to have the probability that it's an 8. Well, if the first one was a 5, then all 4 8s are still in the deck, so that would be 4 out of 51. Okay, plus, now, when I go across a plus sign here, I'm starting back over again with or. Once I reach an or, it means I'm considering the problem fresh, right? So that means I'm back to having all 52 cards in the deck. 4 of those are 8s. And out of the 51 remaining cards, if I drew an 8 the first time, all 4 5s would be in the deck. So it would be 5 out of 51. Right? So that turns out to be 16 out of 2652 plus 16 out of 2652, or 32 out of 2652, which turns out to be 0.0121. So a little over 1% chance of getting one to be a 5 and the other to be an 8. But you have to account for both possible orderings if we're talking about that. Because, and the reason for that is because the second one is conditional, right? So because the second one's conditional, right, that computation is different depending on if I got a 5 first or if I get an 8 first, or at least it could potentially be. Okay. So let's look at the second one. It says 2 fair 6-sided dice, so normal dice, are thrown, and the sum of the 2 dice values is computed. What's the probability that the sum will be a 10? All right, so pause the video and then try it. All right, here's how I would do this. If I'm thinking about the sum of dice, all the different sums that I would get are equally likely to occur, right? Dice don't have any kind of memory or anything. So a really good way is to make a grid of all the possible sums. I could have 1, 2, 3, 4, 5, or 6 for one of the dies, 1, 2, 3, 4, 5, or 6 for the other die, and then what I could do is I could list all the sums in here. So if I had a 1 and a 1, I'd have a 2 as the sum, 2 and a 1 would be a 3, 1 and 3 is a 4. These are all the sums. And it's kind of a very quick grid to kind of put together because it just increases by 1 every time you drop down a row. 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. This is a nice way to list out the entire sample space. So what I'm trying to say is that all the sums are equally likely. So if I want the probability that the sum will be 10, then I'm going to use an equally likely structure. How many total sums are there if I roll a dice? Well, there's 6 times 6. There's 36 total sums possible to choose from. And how many of those would be a 10? 1, 2, 3 of them. So 3 of the 36. So I think the probably most straightforward way to do the problem would be that, and it would turn out to be 0.0833. It's not the only way to do it. This is the idea that we would just consider the sums themselves as the event, and that means this is a single event, right? So we can just use equally likely cases. Now, another way to solve this would be you could consider each of the dice throws independently. That means you're talking about multiple events. So if you're deciding to do it that way, then you're going to be using the and or rules because we're combining multiple events. And it's possible to do it that way too. It's more work, but still possible to do. So let's look at the ways that we could get a 10. We could get a 4 on one dice and a 6 on the other, or we could get a 5 on one dice and a 5 on the other, or we could get a 6 on the first dice and a 4 on the other. And I'm going to list those as separate because they would be separate sums in that grid, right? 4 on the left hand and 6 on the right hand is at one place, and 6 and 4 is a different place, but 5, 5, I don't have to list that one twice because in that grid, that appeared in just a single spot. So if you back up the video a little bit and look at that grid, there's only one spot for 5, 5, but there are separate spots for 4, 6, and 6, 4. So we'll list those three as separate cases. Right, so what's the probability of getting a 4? Well, the sum of 4, right, if I looked at the sum of 4, let me look at the grid again. I'm going to write the grid out. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. The sums are 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7, 8. Actually, sorry, I'm not considering the sums. Let me back that up. I don't have to consider the sums. I need to consider the dice rolls, right? The probability of getting a 4 on a dice roll, these are dice rolls, right? There's a 1 out of 6 chance of getting a 4. And then there's a 1 out of 6 chance of the other dice being a 7, and I would multiply those to get a 4 and a 6. Or, I'll add, there's separately now a 1 out of 6 and 1 out of 6 chance of getting a 5 and a 5. And there's a 1 out of 6 chance of getting a 6 and a 1 out of 6 chance of getting a 4 because there's 6 sides on the dice. So this turns out to be 1 out of 36, 1 out of 36, 1 out of 36, which is 3 out of 36, which is that same 0.0833. So both of those strategies are about equally good. They both involve about the same amount of work. Okay, let's look at the next problem. So this problem says a bag contains 12 quarters, 10 dimes, and 8 nickels. 3 coins are selected without replacement. What's the probability of selecting 3 nickels? What's the probability of selecting one of each coin? So go ahead and give this a try. Pause the video. All right, so for this one, again, I think I'm going to try to kind of look at each individually, each coin that we draw out individually as a different event, and we're going to combine, right? So for this probability of selecting 3 nickels, essentially I need a nickel, and I need a nickel for the second one, and I need a nickel for the third in that order, right? So this is an and case, and we're multiplying. It would be the probability of getting a nickel times the probability of getting a nickel given the first one was a nickel, conditional probability, times the probability of getting a nickel the third time given that the first 2 were nickels. Maybe I could write that like that. Okay, so the probability of getting a nickel the first time would be, well, let's see, we've got, 12 and 8 is 20 plus 10. There's a total of 30 coins here. So out of those 30 coins, 8 of those are nickels, right? But once I've drawn a nickel out, there's 29 coins left, and only 7 of those are nickels. So the conditional probability of getting a nickel the second time, given that we had a nickel the first time, would be only 7 out of the remaining 29. And the same thing true. If I have the condition that I've drawn 2 nickels out, I have 28. And now how many nickels are left? 6. So it would be 8 times 7 times 6, which is 336 on the top. 30 times 29 times 28, which is 24,360 on the bottom. That'd be 0.0138. I think that's the most straightforward way to solve that problem. Okay, and we could take a similar approach to solving the other one. So let me erase this, and we'll do that. The other one, the part B, says we need to have one of each coin. So how many ways can I do that? And since I'm going to do conditional, it means I have to account for the ordering. So we could have a quarter, then the dime, then the nickel, or we could have a quarter, then a nickel, then a dime in that order, or we could have a dime, quarter, nickel, or we could have a dime, nickel, quarter, or I could have the nickel first, then the dime and the quarter, or I could have the nickel, then the quarter, then the dime. Okay? All of those are the ways that that could happen. And so within each of those, I'll multiply some probabilities. The probability of having a quarter first would be 12 out of 30 times the probability of having a dime. Out of the remaining 29, all 10 dimes are still in there, times out of the remaining 28 coins, all 8 nickels are there, right? Plus, this one would be 12 quarters out of 30 times 8 nickels out of the remaining 29 times there are 10 dimes out of the remaining 28. And hopefully you can see that each of these is going to be the same. It's just that the fractions are going to be rearranged. Right, so what I really have is I have 1, 2, 3, 4, 5, 6 cases here that all involve a probability with a 12 and a 10 and an 8 on the top, and a probability with a 30 and a 29 and a 28 on the bottom. So rather than write that completely out, right, because we're going to have enough time spent on this video, that turns out to be this, which is 0.2365. And that's how we would handle that if we were talking about each individual draw and handling them in sequence like that. Okay, now there is another way to do this, and that is if we want to think of this as a single event. If we wanted to think of this as a single event, right, we might talk about the 3 draws all at once, like the selection of the 3 as a single thing, right? Now, if that's true, then it would be equally likely for us to select any 3 coins, right? So I could say the sample space would be the number of ways to select 3 coins without regard to what they are, and the event sample space would be the number of ways to get 3 coins that are different from each other, one of each, right? So the way I could count the number of ways to get the 3 coins is maybe I could use a combination, right? I have a bag of 30 things, they're all distinct, and I'm going to select something and it's going to be used up, so I can't select it again. And the order doesn't matter, they just end up in my hand, so that's a combination. So 30 combination 3, that's how many ways there is for me to select the 3 coins. Okay, for the event space, then I really have to have different coins, right? I have to select a quarter, I have to select a dime, and I have to select a nickel, right? And that means that out of the 12 quarters, I have to select one of those. Out of the 10 dimes, I have to select one of those, and out of the 8 nickels, I have to select one of those. And the multiplication principle says that I could multiply those 2 things together, right? And or those 3 things together. So this probability would end up being 12 choose 1 times 10 choose 1 times 8 choose 1, which is just 12 times 10 times 8, divided by 30 choose 3, which turns out to be 4060. And let me just verify that that is the same. I think it is. So yeah, if I did 30, just to show you where that is, if you did 30, let's do the denominator, 30, math, scroll over to the probability menu, there's NCR, and I choose 3. That's where I'm getting the number 4060. And for example, 12 combination 1 is 12. Okay, so 12 times 10, times 10 times 8 is, yeah, 960. So 960 divided by 4062 turns out to be that same 0.2364. Okay, so that would also be a good way to do it if you wanted to think of it as selection as an entire event rather than looking at the individual coins. And many problems are like this. You can view it as individual events that are ANDed and ORed together, or you can view as equally likely events if you can count the more complicated counting way to count all the ways that that happens. Okay, another problem. A 4-person math club leadership committee will be chosen from 12 boys and 10 girls in the math club. If every person in the club is equally likely to be chosen for the committee, what's the probability that there will be more boys on the committee than girls? So pause this, unpause it, and we'll see if we got it right. Okay, so you know, I think maybe I would just maybe draw a picture here. I've got 12 boys, right? I've got 10 girls, and I'm drawing some of each to make up a committee. It doesn't really matter what order I draw the people in, so most likely combinations are involved here, right? So maybe I could list the ways that I could make a committee, right? I've got a committee of 4 people. So what could happen, right? I could have 4 girls and no boys, right? Or I could have 3 girls and 1 boy, or I could have 2 girls and 2 boys, or I could have 1 girl and 3 boys, or I could have no girls and 4 boys, right? Now, the situation I'm trying to find is the probability that we'll have more boys than girls, right? So this one's out, right? Can't use that one, or this one, because that's the same number. It's only these cases here that have more boys than girls. So I'm really trying to find the probability that we have 1 girl, 3 boys, or 0 girls, 4 boys. And so it's very much like the problem we have with the coins. I would try to figure out, well, let's see. I'm going to do this problem. Let's see. I think well, there's a couple ways we could do it. Let's do it first using the individual, or no, the single event way. So if I think about choosing the committee all at once, then the committees become the things I'm trying to count, right? So the sample space would be the number of ways to make the committee, right? For the committee itself, right? So the number of ways to make the committee would be, if I combine all the people together, there's just 22 people, right? And if I have to choose the people out of that, a combination, 22 choose 4, that would be, there are 7,315 ways to choose 4 people, period, without regard to their gender, right? And then for the samples, or for the event space, right, I have to find the number of ways that meet this particular criteria here, right? So that means that I'm going to have to choose girls and boys, right? And the number of ways to choose these girls would be, I'd be choosing 1 girl, a combination, but I can't choose them out of all 22 people. I can only choose them out of the 10 girls, right? So if you think of it as I'm building a committee of 4, right, people, here's my 4 people, right, here, 4 people. If I'm choosing 1 girl and I'm choosing 3 boys, then they're coming specifically out of just a different set, right? So this 1 girl would be coming out of the 10 girls. And the 3 boys would be chosen out of the 12 boys, okay? And then I would multiply those because of the multiplication principle. And then I could add the other way to do it, which is that out of the 10 girls, I could have no girls, and out of the 12 boys, I could have 4 boys, right? Now that turns out to be, let's see, that turns out to be 10 times 220 plus 1 times 495. And so when you add that up, it's a total of, well, I could add it this way. It's going to end up, the probability is going to be that there are 10 times 220 plus 1 times 495. That's all the ways to get the 4-person committee that meets the special event criteria, divided by the 7,315 total ways to choose the committee if I don't care about gender. Right? And that turns out to be 0.3684. So that would be one way to solve the problem. Okay? All right. Now, if I wanted to instead think of it as a probability combination, right, I could equivalently say that the probability of having more boys than girls is the probability of having specifically 1 girl, 3 boys, plus the probability of having 0 girls, 4 boys, right? And so you could think of this as individual probabilities. It would be 10 times 220 ways to have that specific committee out of the 7,315, plus you could have the probability of this, which was 1 times 495 out of 735. So you can think of it as calculating probabilities separately and then adding them, or you can think of it as calculating the counts separately and then just kind of doing a single probability, right? Both of those come up to be 0.3684. Okay, let's look at the next one. The next problem says 1,000 college students were surveyed and asked about their drinking habits. The following incomplete table shows the number of college students who drink and who do not drink alcohol by gender. So we're only told that there are 500 males that drink and 100 who don't drink. Fill in the missing values in the table, assuming that drinking is independent of gender. So go ahead and pause the video and give this a try. All right, so the idea of independence is that gender here and drinking, the probabilities of drinking should not depend on whether you're a male or female. Right? So really that's like saying the percentage of people who drink should be the same whether I'm talking about males or females or everybody. Right? So the way I would fill this out is maybe since I was given this, I would add this up and say there are 600 people here, right? 600 males. And so what fraction of those people drink? Well, 500 of the 600 people, which it turns out to be, if I compute that in a calculator, 5 out of 6, that turns out to be 0.8333. So the percentage of people of the males who drink is 83.33%, right? So if that, and then the rest of the people do not drink. So if this is supposed to be independent, then the percentage of females who drink has to also be 83.33% exactly, right? So it says there 1,000 college students were surveyed here. So that, by process of elimination there, means that there's 400 females. So if 83.333 of those should drink, all I need to do is take 400 and multiply it by the 0.833 number. 83% of 400 is 333.3. So if I were to round that to the nearest integer, that would be 333 females would drink. And therefore, out of the 400, if we've accounted for 333 of those, 400 minus 333 of those, then the other 67 would have to not drink. Right, so this is the way we would fill the table in so that drinking is independent of gender. It just means that the percentage of people who drink would be the same for males and females, right? That's like saying, that's really saying the probability of drinking given that you're a male is 0.833, and the probability of drinking given that you're female is also 0.8333, right? Right, since those are equal, it's independent. And it also turns out that if you were to add this up, right, this 8, now we've got some rounding error here too, but this would be 833 drinkers total and 167. So if I found the probability of drinking without specifying males or females, that would be 833 out of 1,000, which again is 0.833. Right, so you could check any of those two, and they would be equal if the probabilities are independent. Okay, let's take a look at the next problem. The next one says we have two generic events, A and B. We have the probability of A and probability of B are given, and we're told that they're independent. So we want to find the probability of A or B, A and B, probability of A or B and B there. And we want to ask, are they disjoint? Why or why not, and then find the conditional probabilities A given B and B given A. So pause this and give this a try. All right, so let's look at the first one, probability of A and B. Well, so the probability of A and B, the general formula is this is the symbol for and, right? So let me show you how I remember that. I just think of it this way. If I have A and I have B as separate events, this is the probability of A. This is the probability of B given that A happens. In other words, this is part of a tree here. And this out here would be the probability of A and B happening, both of them happening. Right? So since I know we multiply when we combine and, A has to happen and B, right? It means that the probability of A and B would be the probability of A times the probability of B given that A happened, right? So I think of that tree when I produce the formula, but however, you could memorize the formula too. This is the formula. Now let me write it better there. The probability of A and B would be the probability of A times the probability of B given, B given A. All right, so let's say we got probability of A, that's 0.4. Now, we don't know the probability of B given A. In fact, we're going to compute it. But it did tell me that A and B are independent events. And we found out in the last problem that that means that the probability of A and the probability of B shouldn't change depending on the other one happening. So if this is true, then the probability of B given A should just be the probability of B, period, and also equal to the probability of B given not A. In other words, all the probabilities of B will be the same. And that means I get to replace this probability of B given A with just a simpler probability of B. This is just going to be the probability of B, period. And they did give me that, right? This is 0.4, and this one is 0.3, so it'd be 0.4 times 0.3, and that turns out to be 0.12. So that's the first thing. The probability of A and B is 0.12. Okay, I'm going to go ahead and write this up here, 0.12, and then I'm going to erase this so we can look at the rest of the problems. It says in the next part, find the probability of A union B. So since I have everything as abstract values here, I'm going to use the OR formula for that. The probability, here's how I remember the OR formula. I picture a Venn diagram in my head, and then I remember that if I want the union, the probability of the union, A union B, A or B, it's going to be I should add up what's in the circles for A and B, but I should subtract off what is in the intersection so it doesn't get counted twice. So I use the Venn diagram to help me remember that. But that's the formula I'm going to use, right? And we now know we were given the probability of A, that was 0.4. We were given the probability of B as 0.3. And in part A, we computed that the overlap probability, the AND probability, is 0.12. So then we can add those and subtract and get that the probability of A union B is 0.58. Okay? All right. Then we can ask, are A and B disjoint? Well, disjoint means, or mutually exclusive means there's no overlap. But this probability here, probability of A and B, is 0.12. It's not equal to 0, so therefore there is overlap, so these are not disjoint. You would call this not disjoint, or not mutually exclusive. So the answer to that is not disjoint, and the reason is because there is an overlap. The AND probability is not 0. Okay, for the conditional probability, for C or for D and E, I'm going to use the tree again to kind of produce something. So if I want this, let's do this one. Let's do this one actually. So if I'm looking for the probability of A given B, it kind of implies that if you were to think of these things in order, that B happens first because it's the condition that's determining A. So if I wanted to kind of make a tree, I could put B first. This would be the probability of B. This would be the probability of A given B, right? And this would be the probability of A and B happening together, right? So if I just think of that, maybe populate that tree, then I know that, or I could just use that to make the AND formula. The AND formula, probability of A and B, is equal to the probability of B times the probability of A given B. So I'm trying to solve for this, right? I can solve for that as long as I have the other two quantities, right? We calculated earlier that the probability of A and B is 0.12. We were told the probability of B is 0.3, and so if I just solve this by dividing both sides by 0.3, then the probability of A and B would have to equal 0.12 over 0.3, right? So this would be 0.12 over 0.3, which turns out to be 0.4. 40% chance. So one way would be to essentially use the AND formula, right? Now some people like to use the conditional probability formula. So if I go back to the AND formula here, all the conditional probability formula is doing is pre-solving this for this by dividing both sides by this probability of B. If you divided both sides, you would get the probability of A and B on this side divided by the probability of B. That's equal to the probability of A given B. So some people like to think of that conditional probability formula, and then they just say, okay, so the numerator here is 0.12, which we found before, and then the probability of B was given. So we could use the conditional probability formula for finding that. Okay, for the second one there, I'm going to do that similarly. If I'm trying to find the other conditional probability, so this is the probability of B given A, then I'm thinking this is kind of a range where A is the condition, so it should be first, and then B. This would be the probability of A. This is the probability of B given A, and this is the probability of A and B happening, right? So the AND formula tells me the probability of A and B would be the probability of A times the probability of B given A. And I'm told, or I've calculated that the AND probability is 0.12. Probability of A is 0.4, so the probability of B given A would just be divide both sides by 0.4 there. So it's 0.12 out of 0.4, which turns out to be 0.3. And again, you could write that as a conditional probability by taking this formula and solving it for this to get that the probability of B given A is the probability of A and B divided by the probability of A. Or you could just memorize the conditional probability formula is the AND formula divided by the condition probability. All right, so that would be the way we would compute those. Okay, let's keep going here. Question 7 here says we have two different events, C and D. Probabilities are given. This time we're told that they're disjoint events, and we want to find the probability of C and D, and the probability of C or D, and ask whether or not they're independent, and why or why not. Okay, so pause and give this a try. All right. So, A says, find the probability of C and D. Okay, by definition, disjoint means that there's no overlap, right? That means that C and D cannot be touching each other. This probability would be a probability of an overlap, but there's no overlap at all. So by definition, the answer to that is 0. Okay? Using the OR formula, probability C or D, it's probability of C plus probability of D minus the intersection probability C and D, right? They gave us 0.4 is the probability of C, 0.3 is the probability of D, and we just found out the overlap is 0. So the second part probability would just be 0.7. Okay? And for checking whether C and D are independent, that's a separate question. That has to do with whether the probabilities are staying constant no matter what the other probability is doing. So the best way to solve that, I think, is to find, let's pick one of them. Let's pick C. And we'll say, what's the probability of C? And then we'll also say, what's the probability of C given that D happened? And we'll say, hey, are those probabilities the same? Because if they are the same, then that means that that we don't have to, that means they're independent from each other, right? One is not affecting the other. All right, so so the probability of C is given, that's 0.4. The probability of C given D, well, if I kind of do my tree thing, D would happen first, then C. This is the probability of D. This is the probability of C given D. And this is the probability of C and D. So the probability of C and D is the probability of D times the probability of C given D, right? And I know the probability of D is 0.3, and I know the AND probability we calculated previously to be 0, right? Because there's no overlap because it's disjoint, right? So the probability of C given D, right, would be 0 divided by 0.3. Okay, so this probability here is 0, right? Or you could also just think about it too, right? Picture a Venn diagram that has disjoint events, C and D, right? If D happens, then it's impossible for C to happen, right? Because there's no overlap. There's no way that C and D can happen at the same time. So being disjoint forces, if D happens, it forces the probability of C to be 0. Since those are not equal, it means that these are not independent because the probability of C is changing. In general, it's 40%, but if C happens, then the probability of, or sorry, if D happens, then the probability of C has to be forced to 0, right? And if you did the same thing for the, you could, I mean, I chose to analyze probability of C, but I could just as easily have done probability of D instead. I could say, what's the probability of D? And check, is that the same as the probability of D given C? So the probability of D is given, that's 0.3. If I want the probability of C given, or D given C, C, D, this is the probability of C, this is the probability of D given C, probability of C and D happening, okay? And let me just do it on the tree here. So, well, no, I guess I should write it out. Probability of C and D is the probability of C times the probability of D given C. Let me solve that so it's in the conditional probability form. C and D divided by the probability of C, right? So the probability of C and D is 0 because it's disjoint, and then the probability of C is 0.4. So this probability again is 0, and that means they're not equal, so they're not independent, right? Now, some books, this will be the only time in this video that I explain it this way. Some books talk about a test for independence, and what they say is basically this. They say, okay, the probability of C and D is the probability of C times the probability of D given C, right? So if they were independent, if they were independent, then the probability of D given C would be equal to just the probability of D period. And that means you could simplify the AND formula to get this. You'd say the probability of C and D is equal to the probability of C times the probability of just D, and you don't have to use a conditional probability anymore. Right? So some books say, let's test the simplified version of the AND formula, and if that's true, then that means that they're independent. Okay, so to do it that way, it would say, well, we know this probability is 0, and this probability is 0.4 times 0.3, right? 0.4 times 0.3 turns out to be 0.12, and since those are not equal, then it's not independent. I actually don't like doing it that way. I prefer, and I like my students to do it this way, because this way gets at the heart of what independence means. The simplified AND formula is more of a consequence of independence. It's not really the definition of independence. All right. Next problem. Color blindness is not independent of gender. About 5% of males are colorblind, but only 0.3% of females are colorblind. That's actually true. Assuming the population is evenly split 50% male, 50% female, if a person chosen randomly from a large group of is chosen from a large group of colorblind people, what's the probability that the person chosen is a male? Okay, so pause the video, give this a try. Okay, to me, this is best represented by a tree diagram. And the reason for that is we have two probabilities or percentages. We have percentage of males who are colorblind and percentage of females who are colorblind. And those are conditional probabilities, right? So I can make a tree. The way I'd have to make this tree is first to put the males and females, and then to say, okay, are you colorblind or are you not colorblind? Given that you're that. Now we have to put the male and female first because this 5% of males is the conditional probability given male. So you'd have to be on the male part of the tree for this 5% of males to be colorblind, right? I couldn't list the colorblind one first because then the condition would be in the wrong direction. So trying to make a picture to use the percentage directly, I have to have a tree structured like that. Only 0.3%, so 0.003 is the probability of a colorblind person if the person's a female. Okay, and then we also know 50% and 50% of males are 50% of the population is male and female. So I'm trying to find the probability that a person chosen, okay, it says if a person is chosen from colorblind people. So given that the fact that the person's colorblind, what's the probability that they're a male? This is a conditional probability stated like that. And that means we have to somehow come up with for the denominator something representing colorblindness. So that could be a count or it could be a probability. So the way we get to colorblind is there or there. So the probability of being on this path right here is you'd have to be a male, 50% chance, and, so we're going to multiply by the probability that you're colorblind, which is 5%. Right? You could also have gone down this path, which is there's a 50% chance of being female and then a 0.003 probability of being colorblind there. And because it's this way or this way, we'll add those. Right? So using the and and or rules together, we could say the probability of being colorblind is 0.5 times 0.05. That's the probability of being male and colorblind. Or, so we'll add 50% chance of being a female, 0.003 probability of being colorblind, given that you're a female. Okay, so that represents the conditional sample space. It's a portion of the tree represented as probabilities. Then you could go back and say, okay, how many things meet the event to be the condition to be in the event space? And that would be that you have to go through the male condition. So it's just this one path. So of that, of these things, of these two paths, the one that meets the event criteria is the 0.5 times 0.05. So it's that right there. And if you plug that in your calculator, that turns out to be 0.9434. So given that someone is colorblind, there's a 94% chance that they're male. Okay? Now this is referred to sometimes as a Bayes formula problem because this structure of probabilities of paths within paths, that was discovered by a person named Bayes. But the truth is, I don't view it as a formula at all. I just think of it as a conditional sample space problem. Okay, let's look at another problem here. So this one, a little bit more complicated. It says a game of skill at a county fair consists of throwing ping pong balls into buckets. A game consists of throwing 4 balls at the buckets. In order to win, the player must have all 4 balls land in a bucket. On an individual throw, the ball lands in the bucket 30% of the time. If the player plays this game 1 time, what's the probability they'll win that game? And if the player plays the game 5 times, what's the probability they'll win at least one of the games? So pause this and give it a try. All right, so as I look at this, first thing I'm saying is we'll definitely take one at a time. So for A, maybe what we're talking about is we're talking about the probability that we win, right? So that means we have to win 4 times. Or sorry, we have to get the ball in 4 times, right? So maybe I could say it this way. I could say, let's use the symbol I to mean that a ball goes in the bucket, I for in. And that probability would be 0.3, right? The probability that it's outside would be the other 70% of the time. So 75% of the time the ball goes out of the bucket, 30% it's in. And we're going to make the assumption that each toss of the ball is independent from the previous tosses. Okay, so a win would consist of having in. All 4 have to land in the bucket, right? So since I have to have in and in and in and in, then that means the probability of being in is 30%. The probability of being in the second time is 30% and 30% and 30%. You could write that as 0.3 to the 4th power, and that means the probability is 0.01 of winning. Probability of winning of I, in is about 0.81%. Okay? So the second part of the problem, what we can do is we can say, all right, now we're going to play this game 5 times. What's the probability that we will win at least one of the games? Okay, so now I'm going to switch. I'm now talking not about in and out. I'm going to talk about the probability of winning an individual game. And we just found out from the first part that that probability is 0.0081. So let's say the opposite of that would be losing. The probability of losing would be that. It'll be 1 minus winning, because you can either win or lose. So the probability of losing would be 0.9919. So on an individual game, the probability that I don't get all 4 balls in, that happens 99.19% of the time. All right, so the easiest way to do this problem, since we're talking about winning at least, anytime, so win, let me write it this way, win at least 1 game. The probability of winning at least 1 game in 5, whenever you see at least, you should consider the possibility that it's easier to find the probability of the complement. That could be written as 1 minus the probability of the opposite, right? Winning at least 1 game, right? The opposite of that is that we lose all the games, right? The probability of losing all the games, all 5 games. That's actually easier to find because, right, what we're talking about here is we're playing 5 games and they have to be lose and lose and lose and lose and lose. So that probability of losing would be the 0.9919 probability, except we are going to have to lose 5 games. So we would have 5 of these multiplied together, right? It's 1 minus 0.9919 to the 5th power. And that turns out to be 0.0398. So there's only about a 4% chance that you're going to win at least 1 game, even if you play it 5 times. Okay? Now that's not the only way to solve this, but the other way to solve this part B is much more complicated. I'll go over it quickly, but I would recommend that you do the way that we just did. So if you try to do it by taking account of all the different ways you could win, in other words, you didn't do the complement, you just found the probability of winning at least 1 game and 5, then you'd have to account for all the ways that you could win at least 1 game, right? One way would be to win all 5 games, right? Another way would be to lose a game and win the others. But you'd have to account for every possible ordering of that, right? Something like this. Win, win, lose the 3rd one, win, 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 lose, win, 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 lose. And then you'd have to look at all the ways that you could lose 2 games. Lose, lose, win, win, win. So there are too many to list out. You can't do that directly. But we might be clever about counting how many ways that we could have each of those things happen. How many ways are there to win the game? 5 times. Well, that can happen only one way, right? But how many ways are there to lose the game 1 time, right? In other words, to win 4 times. Well, you can think of that as choosing out of the 5 spots, choosing the 4 spots to win. And so that means that out of the 5 spots, there's 5 choose 4 or 5 combination 4, which turns out to be 5 ways that you can win 4 games and lose 1 game. And you would also have to consider all the ways that you could win 3 games, which turns out to be 10 ways. And then you'd have to consider all the ways to win 2 games, which would be 10 ways again. And you'd have to consider all the ways to win 1 game, which turns out to be 5 ways. Winning 0 games doesn't count because I have to win at least 1 game. And then each of those would have to be multiplied by their probability. So the probability of winning 1 game, right? If we won we won all 5 games, that would be 5 winning probabilities of 0.0081, right? 5 winning probabilities times 1 way for that to happen. For us to win 4, we would have to have 4 winning probabilities multiplied in with 1 losing probability, 9919, and then multiply that by the 5 ways that happens. And then if we won 3 of the games, you'd have to have 3 winning probabilities and 2 losing probabilities all multiplied together, and then multiply by the 10 orderings of ways that could happen. And then you could have that there are 2 winning probabilities and 3 losing probabilities, and multiply that by the 10 ways. And then you could have 1 win and 4 losing ones multiplied by 5, and then add up all of those. Turns out if you do that, you get the exact same thing as we had from doing the complement, but with much, much more work. So the way I remember it is anytime I'm answering a question with the word at least, I at least consider whether the complement is easier to do. It almost always is easier to do. Okay, let's keep going. Number 10, the events A and B occur with the probabilities given. What is the probability of A? Are the events A and B mutually exclusive? Are the events A and B independent? So go ahead and pause this and give this a try. All right, so as I look at this, well, I'm given and or values. I think I'm going to use the or formula, and that's because if you look at the and formula, A and B, it involves a probability and then a conditional probability, B given A, but it doesn't use the or formula or the or probability. But the or formula does use both. So I think let's use the or formula. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B, and then I'll fill in what I know. They told me the probability of B is 0.6. They told me the or probability over here is 0.9. They told me the and probability is 0.2, and that just leaves one thing unknown, which is what I'm trying to solve for, the probability of A. So you could just algebraically solve for this. PA plus 0.4, and so 0.5 would have to be the probability of A. Right, so use the or formula and then solve. Okay, now if you wanted to do that with the Venn diagram, you could do that as well, right? You could say or formulas are Venn diagram problems. We'll generically assume that A and B overlap, and then try to fill out Venn diagrams always from the interior out. So if I know that the and probability is 0.2, that would go in the middle. If the probability of B is 0.6, then filling out the circle, the B circle has to contain 0.6. 0.2 is already there, so 0.4 would be left over there. And then this union would be all 3 of these numbers added up, but we've already accounted for 6 of that. That leaves 30% left to make that 0.9, right? And then we could answer the question probability of A. Now it would just be the 0.3 and the 0.2 added. So you could also do this with the Venn diagram. Although since it's kind of abstract, I felt like it'd probably be just as well to use the formula itself. Okay, so let's go ahead and say, we're going to say that the probability of A is 0.5. And we'll continue. So we're asking whether they're mutually exclusive. Well, so for part B, the probability of A and B is 0.2. It's not 0. So that means that this is not mutually exclusive, right? Mutually exclusive means there's no overlap. And since there is overlap, because the and probability is not 0, that's not mutually exclusive. For independent, we're going to pick one of the variables, like let's say the event B. We'll figure out the probability of event B, and we'll figure out the probability of event B given that A happened, and we'll see if those are equal. And we'll just use that test. So the probability of B is 0.6, that was given. This conditional probability, if I were to write it like A then B, this would be probability of A, probability of B given A, probability of A and B out here. So the probability of A and B is the probability of A times the probability of B given A. And so I know that the probability of A and B is 0.2. I know the probability of A we computed is 0.5, so I should be able to compute this probability. I'll just divide both sides by 0.5. So this is going to end up being 0.2 divided by 0.5, and 0.2 divided by 0.5 is 0.4, and 0.4 and 0.6 are not equal. That means the probability B is changing whether or not A happens, and that means that these are not independent. Okay, let's look at another one. Assume that 24% of adults smoke cigarettes. And then also, let's assume that 16% of smokers develop lung cancer, but 0.2% of non-smokers develop lung cancer. Is developing lung cancer independent of smoking? Explain. What's the probability of developing lung cancer in all adults? And then if a person develops lung cancer, what's the probability that they were a smoker? So pause this and give this one a try. Okay, so for the first one, is the probability of lung cancer independent of smoking? Well, the probability of developing cancer, I'm just going to call it cancer, given that you're a smoker, they said that's 16%, right? The probability of developing cancer, given that you're a non-smoker, maybe I could write it this way, smoker, but I'll put the complement sign, non-smoker, that's 0.2%, right? The fact that those things are not equal means that the probability of having cancer depends on whether you're a smoker, and therefore these are not independent. These are not independent because in fact they do depend on whether you smoke. Okay, and then it says, what's the probability of developing lung cancer in all smokers? So I think, again, because I'm given percentages as condition of smoking or not, we can make a tree. And let's first start with someone either smokes or they do not smoke. And then, so they're a smoker or they're not a smoker. And then they could have the cancer, the lung cancer, or they cannot have the cancer, right? They can have cancer or not have cancer. Right? And we know that it says 24% of adults smoke, so 24% smoke. That means that the other 76% of people do not smoke. If you are a smoker, then 16% chance of having cancer. So that's that conditional probability. If you don't smoke, 0.002 is the probability of having the lung cancer. Okay, so what's the probability of developing lung cancer, period? So for that problem, we would just say you could develop cancer this way or this way. So if I'm a smoker and cancer, that would be 0.24% smoker times 0.16 there of having cancer if you're a smoker. Or you could be the 76% of people who don't smoke and one of the 0.2% of people who get cancer even though they don't smoke. And then it could be this way or this way. So the probability of having cancer, period, is going to be 0.24 times 0.16, that's and, plus for or, the 0.76 times 0.002. And that turns out to be 0.0399. So the percentage of people who have lung cancer, period, in the whole population is about 4%. If a person develops lung cancer, then what is the probability that they are a smoker? So this is a conditional probability. What's the probability that they were a smoker, given that we know that they developed cancer? Okay, so we're going to have a fraction here, and the bottom is going to be everything related to the condition cancer. So the condition cancer is this path leads to cancer, right? And this path also leads to cancer. So the total probability of cancer is what we found out right here. It's the 0.24 times 0.16 plus 0.76 times 0.002. So you can think of it as two paths. And then the question is, okay, out of those two paths, which ones resulted in we were smokers. That would be this one only. So only this path here, only the 0.24 times 0.16 path came through the smoker event condition there. All right, so it would be that fraction right there. It'd be 0.24 times 0.16. It'd be, right, this probability divided by both the probabilities. This probability out of both probabilities. And that turns out to be 0.9619. So if you do have lung cancer in this town, there was a 96% chance that you were a smoker. Okay, let's keep going here. A person is dealt 4 cards from a standard deck of 52 cards. What's the probability that they are all clubs, all diamonds, or all hearts? So pause this and give this a try. Okay, I think I would write it this way, right? The first card would have to be a club, and the second card club, and the third card club, and the fourth card club, or we could have diamond, then diamond, then diamond, then diamond, or we could have heart, then heart, then heart, then heart. And we'll use and or rules. So the probability that the first card is a club, well, 13 of the 52 cards, 1/4 of the deck is clubs. If we've taken one card out, we have 51 cards left. 12 of the clubs are left to be in there, right? Out of the remaining 50 cards, 11 of those are clubs, and out of the remaining 49 clubs or cards, 10 of those are clubs. So I would multiply those to find the probability of specific having the 4 clubs. Or plus, and now since I'm ORing, this is a brand new look at the problem. We're back to having the full deck. We would have 52 cards, 13 of them are diamonds. Out of the remaining 51 cards, 12 are diamonds. And the same structure here, whether we're talking about clubs or diamonds, right? So same thing. Plus, I would have another one that's the same, right? 13 out of 52, 12 out of 51, 11 out of 50, and 10 out of 49. So if you multiply those out and then add the results, ends up getting 0.0079. The important point here is that every time you start with an or, you go or, that's a completely separate way to meet the event criteria. So you have to go back to the fresh deck. All right, number 13. A pair of fair 6-sided die are tossed 2 times. Find the probability that a sum of 9 or higher appears at least twice. Okay, so give this one a try. All right, so when we're talking about the sum of dice, a grid is a good way to picture that. So we're looking at the sums. We could have a 1, 2, 3, 4, 5, or 6 for the one die, 1, 2, 3, 4, 5, or 6 for the other die, and in here I can list the sums. A 1 and 1 has a sum of 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. Okay, so there are 36 outcomes there, and if I'm finding the probability that an individual toss has a sum of 9 or higher, well, 9 or higher would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those cases. So that probability turns out to be 0.2778. That's the probability of a toss, a single toss having a sum of 9 or higher. So this says we're going to now toss the dice 2 times, and we want to find the probability that that happens at least twice. So let's use this symbol. Let's use the symbol Y to mean that the sum is 9 or higher, and we'll use the symbol N to mean that the sum was less than 9. Okay? So what could happen if I toss the dice twice? I could have 0 of the tosses, and let's see, it's 2 times? Yeah, 2 times. Yeah, okay, so 0 could be yes, right? Or, and both of them could be no, right? Or I could have that one of them was yes, one of the times I tossed was yes, and one of them was no. In other words, I got a sum of 9 the first time, but I didn't get a sum of 9 or higher the second time. Or I could have 2 of them are yes, and none of them are no. Both of the times they could be a sum of higher. So I want to find the probability that it's at least twice, That doesn't really make a lot of sense. Let me change the problem slightly. I think I initially intended for this to be that we toss the dice 4 times, so I apologize for that. Let's ask the question, what if I toss the dice 4 times? Then what would the probability be that it was at least twice? So if I wanted to add that on, it adds some complication here, because now there's 4 things that can happen. So it could be you'd have 0 yeses and all 4 are no, or 1 could be a yes and 3 of the dice tosses could be no's, or 2 are yes and 2 are no's, or 3 are yes and 1 is no, or all 4 of them are yes and 0 are no, where yes means that that particular pair of dice toss has a sum of 9 or higher. Okay, so that if I had this happen at least twice, that would be these cases over here, right? So the probability here for 2 yeses and 2 no's would be 2 yes probabilities, right? So the probability of yes here, we found out is the probability of a yes is 0.2778, right? That's the probability the sum is 9 or higher. So the probability of a no would just be 1 minus that. The other, well, let's see, that would be the other 72.22%. So if I have 2 yes probabilities and 2 no probabilities in that order, it would be 0.2778 twice, and there would be a 0.7222 twice, right? This case here, or we have 3 yeses and 1 no, so we would have 3 yes probabilities, 0.2778 3 times, and then 1 no probability, right? And then this one, the 4 yeses and the 0 no's, 0.2778 yes, and there's no probability, so I don't have to multiply that. And I am going to add here, but there's a complication, right? And that is that this 2 yes and 2 no thing, right, that can happen in a lot of different ways. It could be the first 2 are yes and the second 2 are no. It could be yes, no, yes, no. It could be, no, yes, yes, no, right? So how many ways are there to have that happen? The best way, rather than trying to list them, is to say out of the 4 spots, we have to pick 2 of them to contain yeses. So that means out of the 4 spots, if I choose 2 without caring what order which ones I choose first to be the yeses, there's 4 choose 2 or 6 ways that this can happen. So I have to multiply this probability by 6 because there's 6 ways that can happen. Right here, I would be out of the 4 spots choosing 3 to be the yeses, which is 4. So I have to multiply that by 4. And then here, there's only one way that can happen, if it's yes, 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 yes. So only one way. So in fact, this is the statement that would give me this probability. Not at all obvious, right? But the probability turns out to be 0.3094. All right. Okay, let's move on. Just a few left here. So for this one, it says in a small city, the probability of having throat cancer in the population is 4%. A test for throat cancer is positive 92% of the time if a person has throat cancer. If a person does not have throat cancer, the test gives a false positive 10% of the time. If a person tests positive for throat cancer, what's the probability that they do have throat cancer? And then secondly, if the person is given the test twice, if they test positive, and they test positive the second time as well, then what's the probability that they do have throat cancer? So pause that one and give it a try. All right, I think this one definitely going to require that we use a tree. Let's see, we could either have cancer, have this throat cancer, or a person could not have the cancer. And the probability of having this cancer is 4% of the population, so 96% of the people don't. Wow, this is a really virulent cancer if 4% of the people have it. Okay, and then let's see, if we have this test, the test could be positive or the test could be negative. And if you do have cancer, there's a 92% chance that the test will catch that. If we don't have cancer, there's a 10% chance of a false positive, right? So we're trying to figure out what's the probability that if you test, so given that you tested positive, what's the probability that you actually have the cancer? So this is going to be a probability of paths, like a Bayes formula problem, right? So all the different ways to test positive on the bottom here, we test positive this way and this way. So I'm really finding the probability of testing positive, period, right? And that is going to be, we could have 4% chance of having cancer and 92% chance of catching it with the test, plus, or we could be in the 96% of the population that doesn't have the cancer, but have it in the 10% of the population that has a false positive. And then out of that, right, which of those paths went through the cancer spot? That would be just out of these two paths, the one that is cancer is 0.04 times 0.92. That is the probability that you have cancer and are positive, right? So the conditional probability formula, or you can think of it as a tree probability. And that probability turns out to be 0.2771. So maybe you calculated and you said there's no way that's right. But actually that's correct. If you have this cancer, if you tested positive, and then there's only a 28% chance that you actually have the cancer. Wow. So that's kind of scary. Why is it so high? The reason why is because of this false positive being 10%, right? Most of the positive tests are actually going to come through the lower path, right? The lower path, 96% of the people are on that path, but 10% of them test positive. So most of the tests that are positive are false positives, or at least 27% are, right? So there's a much higher chance that you have this from well, it's not 27%, but there's a higher probability that than you would think of having a false positive. And it's because so many people don't have this cancer. Okay, the second one says, what if we give the test twice? So what if you have this, you're tested again, and you have the same probabilities of being a positive test or a false positive. So now what is the probability of having cancer given that you tested twice positive? So this time it would be the probability of the paths of probability of cancer is 0.04 of having cancer. You'd have to test positive and test positive a second time. Or, so plus, you could not have cancer, 10% chance of a false positive times 10% chance the second one is also a false positive. And of that, the probability of being in the path that had cancer was only the left path there, the top path, 0.04 times 0.92 times 0.92. And that one turns out to be 0.7791. So if I test positive twice, my confidence has increased to 78% that I have the cancer. And that's even still not very high. We might even order a third test with this test because it has such a high false positive. The reason why this is so shocking is because of the high false positive rate, right? And the fact that most of the people actually don't have cancer. So if you're testing positive, it's a pretty good likelihood that you're testing positive because of the false positive. All right, continuing here. There are 3 cashiers, Alicia, Brian, and Charlie, working at a particular hardware store. Occasionally, cashiers miss an item in the customer's basket and undercharge the customer, which results in lost income for the store. Alicia undercharges customers 1% of the time. Brian undercharges customers 2% of the time. Charlie undercharges customers 3% of the time. If a customer is randomly selected from the list of customers who were undercharged, what's the probability that it was Brian who undercharged them? So give this one a shot. All right. Again, I think this is a tree problem. You could have Alicia, Brian, or Charlie that waited on people here. And if Alicia works with them, you could undercharge or not undercharge. You could undercharge or not undercharge. Undercharge or not undercharge. And the chances 1% for Alicia, 2% for Brian, 3% for Charlie. Now, for us to solve this problem, we have to know what the probabilities are of these partitions, this A, B, and C here. So let's make the assumption that they're all equally likely to be the person that waited on them. That makes these probabilities all 1/3, okay? So what we're trying to find is, given that they're undercharged, what's the probability that it was Brian who undercharged them? All right, so let's see. So all the ways to be undercharged would be 1/3 of the chance Alicia with a 1% chance of undercharging, 1/3 of a chance Brian with a 2% chance of undercharging, 1/3 of a chance of Charlie with a 3% chance of undercharging. And of those 3 paths, only the one, this one here is the one that meant Brian was the one that did it. So 1/3 times 0.02. So the idea here is that this Bayes formula structure can be used with any number of paths. So that would be the setup to find it, and very similar to the problems we just did. It would turn out to be actually 1/3 of a chance that it was the Brian customer, or the Brian cashier. Okay, let's move on here. In a shipment of 20 televisions, 6 are known to be defective. If 10 televisions are selected at random, then what's the probability that all 10 are defective? All right, so pause that, give it a try. All right, so when I'm looking at this problem, I'm kind of picturing this. There's 20 TVs, 6 of them are defective, right? That means that there are 14 that are not defective, that are good, right? And I'm going to select 10 out of all of this, right? And some of them are going to be defective and some of them are going to be not defective, okay? Which really means that we're going to have to select the not defective ones out of the 14 not defective ones and the defective ones out of the 6 that are defective. So we're trying to find the probability that all 10 are defective, right? So that would be 10 here, all 10, and 0 are not defective, okay? But I see an issue here. Do you see it? We would have to select 10 defective TVs out of only 6. That's not possible, right? We can't get 10 defective TVs if there's only 6 defective TVs. So by inspection, this probability of having all 10 defective, right, that would be 0. Almost a trick question. Okay, let's move on. If, let's say for a 4-child family, we want to find the probability of the family having exactly 1 boy, given that the first child is a girl. All right. Let's see. Yeah, go ahead and pause this and try the problem. So I think of this kind of as a tree problem, although we wouldn't have to do that. You could do it with a tree. You could say, I could have a girl, boy, girl, boy, girl, boy. Actually, you know what? With 4 people, the tree is getting kind of unwieldy. So let's just not do a tree. Initially, I was thinking a tree, but maybe not. Maybe we could just list out the different ways that we could have the exactly 1 boy, given that the first one's a girl, right? So I could list things like this, like the first one's a girl, the second one's a boy, the third one's a boy, the fourth one's a girl, in that order, right? So what I'm really saying is, I don't really care what the first child is. I'm interested, well, actually I'm saying, given the first child is a girl, so the first child is definitely a girl, okay? But what's the probability that I would have exactly 1 boy in the remaining children? So these children we're not sure what they are. They could be boys or girls, but the first one's definitely a girl. Okay, so maybe I could think of this as equally likely. Presumably, it's equally likely to have boys and girls, so every possible grouping of boys and girls is equally likely. We could treat this as an equally likely case. We're finding the probability of having exactly 1 boy, right? So the sample space would be the number of ways to choose the 4 children. So what would that be? Well, there's 4 kids to choose. We're told that the first one's definitely a girl, so there's only 1 way to choose that, right? But the second one could be a girl or a boy, girl or a boy, girl or a boy. So that means there's 8 different combinations of families to choose that force the first one to be a girl, right? And then the event would be the number of ways to have exactly 1 boy. Exactly 1 boy. So if I listed it that way, the first one is chosen for us, that's a girl, right? But how many ways could I have if only 1 is a boy? Well, I think I'm going to have to resort to listing this out. I could have the boy first and then girl, girl, or I could have the girl first, then the boy, then the girl, or I could have the girl, then the boy, right? So if I kind of list out specifically, it looks to me like there are 3 ways that could be done, right? So 3 of the orderings have 1 boy, and 8 of the orderings have any number of boys after the first girl. So that probability would be 3/8, or 0.375. Okay? There may be other strategies, but I think that's probably the best way to think of it. Okay, let's look at another one. For a certain type of epilepsy, a child of parents with epilepsy has a 10% chance of inheriting the disease. And this probability is independent from one child to child of the parents. If the parents with epilepsy have 2 children, what's the probability that both children will have epilepsy? What's the probability that neither child has epilepsy? What's the probability that exactly 1 child will have epilepsy? Okay, so pause this. This is our last problem, and then we'll go ahead and try this. All right, so when I look at this, I'm kind of thinking we're talking about both, neither, exactly. We haven't seen like a full probability model. Let's do this by writing out a probability model. So I'm going to make a probability model. I'm going to use the symbol E to mean that an individual child has epilepsy, and I'll use not E for not having epilepsy. Okay, so what are the possibilities if we have, let's see, 2 children? Well, I'm really interested in how many of the children have epilepsy. So let's make a random variable, I'll call it X, that represents the number of their children who have epilepsy. Okay, so the possibilities are they could have no children at all, which specifically would be the first child does not and the second child does not, or they could have one child, which means the first one does and the second one doesn't, or the first one doesn't and the second one does, or both of them could have epilepsy, which means it would be that they both did. All right, so what are the probabilities associated with that? Maybe we could go ahead and fill in this probability chart here. Well, if it says that the probability of having epilepsy is 10% and it's independent, then the probability would be 0.1 of E happening. And that means that the probability of E not happening would be 1 minus that, which would be a 90% chance that a child doesn't have it. So for the family to have 0 children have it, then that would be 90% chance that the first one does not and 90% chance that the second one does not, which turns out to be 81% of the time neither child will have epilepsy. Okay, for this case here, the first child would have it, which is 10%, times and the second child would not. So that would be multiply, or, so we'll add, the first child could not have it and the second child could, so 0.1, those would be multiplied. And when we multiply and add, that turns out to be 18% chance of one or the other child having it. And then for the last case where there were 2, they would both have to have it, which is the probability 10%. So 10% times 10% is 1%. Now, if this is right, if this is a valid probability model, if I add these 3 numbers up, they should add up to 1, and they do. That means I've correctly accounted for all the cases here. Now I can use that to answer the questions. So the first one is the probability of having both children. That's 2, and that probability would be 1%. The second one is the probability that neither child would have it. That would be 0, and that's the 0.18. And then the third one is the probability that exactly 1 will have it, and that's the middle one, which is, this is 81%, and 18% for the last one. All right. Okay, so that's pretty good sampling of different kinds of problems that you can see that involve and or used together. Thank you for watching these videos.